Hello, this is Colton Gomel presenting the virtual version of my generation of reference data from BackPack LiDAR point clouds for quality control of tree inventory products poster. I'm the primary author of this presentation, but would like to acknowledge Dr. Song-Yoon Park and Hazem Hanafi for their contributions, as well as my mentor, Dr. Habib. Starting with a little background on me, I'm an undergraduate student at Purdue University majoring in civil engineering with a concentration in geomatics and a minor in anthropology. This is my second year where I've been able to perform research for Purdue's Institute for Digital Forestry as a member of Dr. Habib's Digital Photogrammetry Research Group, or DPRG. Forests play an important role in the environment and in the economy. In Indiana alone, the forest product industry produces $10 billion of value every year and is responsible for 70,000 jobs, according to the USDA Forest Service's Indiana Forests 2018 Summary Report. Forests also cover approximately 1/5 of the total land of Indiana. In order to assess their tree inventories, forest and plantation owners use many tree biometrics, including diameter at breast height and merchantable height. These tree biometrics have traditionally been collected by workers going into the field and using calipers or a tape measure as pictured to measure individual tree DBHs. This means workers can only measure one tree at a time, and large inventories are impractical to measure due to intensive labor required and associated costs. However, recent improvements in accessibility of LiDAR technology has made possible new ways to measure tree inventories to get tree biometrics. By integrating LiDAR and GNSS/IMU units into Mobile Mapping System, or MMS, it is possible to collect accurate geolocated point clouds of forested environments. DPRG has developed many such backpack MMSs, such as the KNAP. DPRG is also currently developing a forest biometric pipeline to automatically segment individual trees from point cloud data and derive key biometrics such as DBH, as well as the tree's location, more efficiently in order to allow for less labor-intensive and expensive tree inventory assessment. The pipeline is still in development, and as such, quality control is needed to find possible improvements. Ground truth reference maps, however, are not always accessible or are difficult to collect. To remedy this, a methodology was developed to obtain pseudo-reference maps from input point cloud data. This methodology was tested on 5 datasets, obtained from 3 mission areas at UGA Whitehall's forest in Athens, Georgia, from May 11th and May 15th through 16th in 2025. A total of 5 datasets were used, being collected using DPRG's KNAP and the commercial Hovermap backpack systems. 2 of these areas were plantation and 1 was a natural growth forest. These datasets include a seed orchard, which was collected using KNAP and KNAP on an all-terrain vehicle, a loblolly plantation, which was collected using KNAP, and the GPS course, which was collected using both KNAP and Hovermap. The methodology to obtain the pseudo-reference map is as such. The point cloud is first height normalized, and a horizontal slice encompassing breast height 1.3 meters to 1.8 meters is isolated. A DB scan-based approach is then used to automatically cluster the slice data into stem and outlier or non-stem clusters. Manual refinement of the initial clustering is required, so Cloud Compare is employed to recover missing stems initially classified as outlier and to refine the initial stem clusters by removing misidentified outlier using the manual segmentation tool. Stem clusters with DPHs measured within Cloud Compare that were less than 4 inches or 0.102 meters are also removed manually. The refined and recovered stem clusters are combined and then checked against the initial slice data to determine if stem clusters were accidentally removed during the process. Once checked and any removed stems are recovered, the final reference map is created by combining all the stem clusters together. Least squares-based circle fitting is then used to derive DBH and stem locations from clusters. Trees with DBHs of less than 4 inches from the least squares-based circle fitting are removed from the dataset before comparison with pipeline results. Tree locations are then compared with pipeline results within a buffer of 0.25 meters around the point. Pipeline points that were in the buffer were marked as true positive. Those associated with no reference map center were marked as false positives, and reference map centers with no pipeline result were denoted as false negatives. These recordings were used to calculate the precision, recall, and F1 scores. Trunks with correct geolocation and DBH circle fitting confidences of greater than 50% were then compared, with the mean absolute difference, standard deviation, and root mean square error being calculated. These results showed key insights into the pipeline. The seed orchard pedestrian KNAP dataset showed the small trees were being removed as understory. The analysis of the seed orchard ATV KNAP dataset showed snags were being removed as understory incorrectly. A false negative point in the loblolly plantation dataset showed that a stem had been misidentified as foliage, resulting in the stem being associated with another tree and missing many points. The false negatives can also show how difficult detecting some trees can be. In the GPS course pedestrian KNAP dataset, false negative shows a tree was missed due to a sparse stem and understory blocking the lower part of the tree, which created an occlusion. A large cluster of false positives in the GPS course Hovermap dataset showed the pipeline was over-segmenting some trees, resulting in single trees being identified as multiple. In comparing stem locations between the reference maps and the pipeline results from Seed Orchard ATV have the highest precision at 98.6%, recall at 97.4%, and F1 score at 97.2%. GPS course KNAP had the lowest precision F1 score at 80.9% and 86.7% respectively, but loblolly plantation had the lowest recall score at 88.3%. In DBH analysis, the mean absolute difference between the pipeline result and the reference map ranged from 0.79 centimeters to 1.71 centimeters, with standard deviations from 0.96 to 2.05 centimeters, and a root mean square error from 1.24 centimeters to 2.67 centimeters. Results showed that the pipeline had some difficulties with missing trees and over-segmentation. These issues were documented, reported, and being resolved through improvements to the pipeline. The methodology allowed for quick and iterative discoveries of ways to improve the pipeline in the absence of accessible or easy-to-collect ground truth. The tree inventory pipeline results had higher precision for plantation than natural forest, likely as the spacing between trees, less undergrowth, and less trees with small diameters increased the false positive results from the pipeline. Recall differed less between environments with possibly higher average values for forest datasets. Improved clustering algorithms could reduce processing time even further, as manual refinement of initial results made up most of the time spent on each dataset. I would like to acknowledge Perseus for supporting this work, as well as the Institute of Digital Forestry and the Digital Photogrammetry Research Group. Thank you.